Assalamualaikum
Warahmatullahi
warahmatullahi wabarakatuh.
wabarakatuh.
Good morning, ladies and gentlemen. It's a great pleasure to welcome all of you on the second day of the 9th International Symposium on Applied Chemistry 2023 in conjunction with the 5th International Conference on Chemical and Material Engineering. Still with us, Diki Anas and Reza Audina Putri as the Master of Ceremony.
Ladies and gentlemen, today the agenda of our symposium are sponsorship presentation, 2 plenary session, and also 2 parallel session at noon. We would like to thanks to our sponsor, PT LMS Indonesia,
PT Era Mitra Perdana,
Dynatek,
Biolab Science Universal,
PT Serviam Abadi Murni,
Horiba Scientific,
Science Analytica Prima,
Garuda Food,
Teknolab,
and Elo Karsa Utama.
Ladies and gentlemen, and our honorable guests, there are several announcements to online participants. First, please have a stable connection.
Second, make sure that your computer has a working camera and audio device.
Third, the host will automatically mute the audio of all participants.
Fourth, the chat room is only available for delivering questions to the ongoing discussion in the session and announcements delivered by the organizing committees.
Fifth, please ensure to properly rename your Zoom ID by your name and your credentials according to your participation category to set you up to the correct breakout room in the parallel session.
And for the on-site participants, please try to limit distraction like the smartphone during your plenary session.
For both on-site and online participants, do not forget to fulfill the list of attendees that we share in the chat room or in the link tree.
Ladies and gentlemen, we will start the symposium by the presentation by one of our sponsors, PT Era Mitra Perdana. We have Mrs. Ruby Huey, who will present about advanced pore size analysis of microporous and ultra microporous materials. On this session will be moderated by Dr. Kiki Cornelia Sari Sembiring, Master of Engineering.
Dr. Kiki Cornelia Sari Sembiring, Master of Engineering, is a senior researcher at National Research and Innovation Agency, BRIN, Indonesia. She got her master's degree in applied chemistry and biotechnology from Chiba University, Japan, and Ph.D. degree from Energy Science, Kyoto University, Japan. Her expertise are catalysts and renewable energy. Now, Dr. Kiki Cornelia Sari Sembiring, Master of Engineering is a researcher at a Research Center for Chemistry, BRIN. She has many publications, book chapters, and patents related to her expertise.
Well, ladies and gentlemen, I will give time to our moderators, Dr. Kiki Cornelia Sari Sembiring, Master of Engineering. The time is yours.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. I am Kiki Cornelia Sari Sembiring. It is my huge pleasure that I'm here as a moderator for this section. Here with us today, we have Ms. Ruby Hui from Micromeritics Instrument Corporation. So let me invite Ms. Ruby to join me on the stage. So welcome to ISAC and in conjunction with ICCME 2003, Misri. So before Miss Ruby deliver her presentation today, let me introduce her. Miss Ruby achieved her bachelor degree in chemical technology from National University of Malaysia, and she has considerable professional experiences, more than 15 years, in bridging analytical instrument solutions to industries, and she has joined Micromeritics in 2002. And also anyone here or online participants will have opportunity to ask questions in the last part of this section. So, Miss Ruby, please, the time is yours.
Thank you very much, Dr. Kiki. Good morning, selamat pagi to everyone. I'm Ruby Hui from Micromeritics. May I know how to change to my slide? Okay, thank you very much. Maybe I'll use the stage over there. Hi, okay. So today my sharing about advanced process analysis of microporous materials. So as what you can see over here, catalysts involve a lot of different pore sizes, and the pore size distribution can be varies from micropore, mesoporous, microporous to even ultra microporous as well, with a lot of different applications of it. So today my sharings will mainly focus on micropore, which is less than 2 nanometers, and for the ultra microporous will be less than 0.3 nanometers, where we also have a suitable solutions to address to the characterizations of it. So with microporous characterizations is widely being used by the characterizations are used, using microphysics option method to characterize the micropores samples. So what is physics option? So in physics options over here is a physics option absorption, where it's a non-selected selective adhesions of adsorbate to the absorbent. So the samples will be the absorbent, and the gases will be the adsorbate to adhesions onto it using van der Waals forces. The heat of adsorptions are greater than the heat of vaporizations. And in physics options is affected by the temperature, pressure, and surface structure. So taking this advantage of the surface structures, we are able to use it to analyze the cryogenic at cryogenic temperature, where it allows the gas to dope onto the different surfaces. Very common adsorptive gas are using nitrogen, krypton, carbon dioxide, and argon. So just a quick one on how the physics option works is when we go on to very low pressure, we are clearing all the gases on the surface of the samples, and we start to adhere different gas onto it. The first stage at low pressure, it will be an isolated absorption, okay, and it slowly form one layer of it in stage 2. And in stage 3, we continue increasing the gas pressure. It will be reaching stage 3, where they will form multi-layers. And at stage 4, it will start with the pore fillings. So as we increase the pressure from low to high, we are undergoing this physics option of doping different gases onto the surface of the samples. So, oops. A static monometric gas absorption, a simple apparatus to address to these physics options is where we have a sample that is evacuated, where we remove the existing gases on the surface. The sample holder are immersed in a constant temperature bath, maybe at cryogenic temperature or at 0 degrees Celsius. or 273 Kelvin. So a known quantity of gas is emitted to the confined sample holder. So the pressure will fall as the gas absorbed on the surface and as it reach equilibrium. Successive dosing will require depending on how much the sample can absorb. Increasing or decreasing pressure incrementally to collect the quantity of the absorbed at each pressure. So this is a simple schematic on what happened during a gas absorption. Allow me to share a little bit on our instruments schematic, where it involve vacuum pump, where we are able to remove the sample of the surface of the samples, okay, degassing it and so on. And there will be servo valve, sample valve, absorptive valve, vacuum valve involved, and also a pressure transducer to control the pressure within the sample holder itself. There's manifold, thermocouple, and sample tube. So after the entire apparatus being set up, what is being measured is pressure and temperature. So what will happen over here, that we are using this direct measurement for a PV equals to nRT equation over here to get the quantity absorbed.
Recording in progress.
Thank you. Oops. It's not switching slide. Oops. So what is the obtained data that you will see will be an isotherm. So a lot of papers have been sharing about the isotherm, which is a quantity of the absorptive gas absorbed on the sample at varying pressure at constant temperature. Oops. So in isotherm, as per IUPAC, it has different patterns as well, different type of it. So at microporous, what you'll be seeing is the absorptive and the desorptive as the type 1. So that will be the microporous. If you are able to get this in the isotherm, your samples does consist microporous inside. But some samples may not only having micropores, it might have a mixture of micropores and mesopores as well. So what kind of informations can we get on an isotherm over here? We are able to get surface area, pore size distribution, pore volume as well. So over here you can see BET, which is a very common one to measure on the surface area. There is also other models as in T-plot, BJH, and also the HK, Hoven-Cavazo for the micropore filling. So if you would like to have a quick, simple information about surface area, you can run at a smaller pressure range to get a PET. But if you would like to have a better picture of the samples, you can run a full isotherm that will require slightly longer experiment time. Okay, especially at the micropore area. So just a quick one on the BET, which is Bronner, Omete, and Teller. It's a Langmuir model that started in been designed in 1932. So it's a well-established models available, and the overlaying at the point B is a monolayer completions and the start of the multi-layer. So this is where you are able to see the transitions of it. And in BET, in microporous sample on microactive software is quite easy that you are able to extract the data as well. Okay, so moving forward, if you were to continue the pressure to a higher pressure, you'll be able to analyze T-plot. So in T-plot model, what you are able to get is starting to have is using the T curve is used for the T-plot and the BJH or BJH, where you are looking at the multi-layers or starting filling of multi-layers. And from there, you are able to estimate the micropore volume and to estimate the external surface area of the sample. So this is to estimate the presence of micropore volume and the external surface area. So the linear region after the micropore filling or before the capillary condensations are able to analyze using T-plot. So it's oversimplified model and not accounting for the micropore filling. But T-plot is widely used and is a good estimation to estimate the presence of the micropore in a sample. So I would say it's maybe like a screening test that you are able to check whether your samples consist or do not consist any micropore, because it's important in the way of how you synthesize the catalyst. So T-plots, there is also different expressions available on the thickness equations. So they are all available over here, and you are able to use it to predict on the thickness as well. So the T-plot is available on the TreeFlex software, one of our instrument software over here, to quickly check whether is there a micropores available in the samples. Okay. And moving forward, as we increase the pressure to an even wider range, you're able to cover BJH, Barrett, Joyner, and Highlander. Okay. So this is a very good model to look into the mesopore size distribution between 2 to 10 nanometers. So it's able to address the radius of the, oh, it's a bit far. Okay, so you are able to look into it, that is able to look into the micropore size distributions. Okay. And it can be in BJH absorption or desorption. So looking into the micropore filling, this is the one that is taking the longest time in the experiment, where we need to actually prepare the samples or the environment at a very low pressure. So this we will be able to look into the Howard-Cavazzo model for the micropore filling. So the micropore distributions is about 2 nanometers in slit pores. You are able to use HK model. So it's originally developed for micropore size characterizations from nitrogen isotopes on molecular sieve carbons. So it's very established and easy to use fittings, model fittings. So it's a very first method that accurately accounted for the absorbate interactions between that within the parameters. So it's based on the model of the Everett and Powell to describe the potential energy on the single molecules between 2 parallel planes. However, with this, the pores are always completely filled or completely empty when we desorb them. So there is some assumptions as well that the questionable assumptions is always there with the HK model, but it's widely used and acceptable. So apart on using HK for the micropore distributions, it also has a further extension to cytophoray. So cytophoray is to look into cylindrical pores. So just now we look into the slit pores. This is for cylindrical pores. So this assumes that the cylindrical pores are perfect at infinite length. So there are some assumptions involved in the HK extension using cytophoray models. So there is also another extension from HK model, Chengyang, where it's actually looking into the micropores less than 2 nanometers for spherical pores. So the pores might have different shapes and so on. So we are using different models to try to address to them, but this assumption is accounted for non-linearity of the type 1 isotherm with the Langmuir model. So it assumed the exclusive interactions of the absorptive molecules with oxygen atoms, and the pore walls is consisted of a single planar lattice. So all these models are very well established, and yet each models have some assumption involved in micropores. So in the HK models, in the microactive software, it's very easy to use as well. You are able to select the pore geometry, whether it's a slit, a cylindrical, or sphere. So you can just select from the pore geometry over there to look into the micropore size distribution. However, looking at the assumptions involved, although gas absorption is well-established technique for porosity characterization, but the application is become more challenging at the micropores region because the pore geometry might be different whenever you synthesize a sample. So how we are able to further or better characterization of the micropore spike is to look into using non-local density functional theory, NLDFT. This is a new and improved models for enhanced characterizations of porous materials such as carbon, zeolite, or MOFs. So it's to refine the performance of the gas absorption technique for materials with micropore structure. So it involves molecular modeling to generate more accurate value. The relevant NLDFT models therefore play a crucial part to convert a lot of this modeling as well, and these models are available free of charge for customers. So help our customers or help our users over here, we are extending the use of argon as sorptive for carbon and zeolite to address the well-documented limitations if you use nitrogen as absorbate for micropores material. Oops. Okay, so it also enhance, we also have another type of NLDFT model to enhance the use of oxygen as the sorptive gas for carbon. For micropore analysis of oxygens is less expensive and also became an alternative to argon with superior performance to nitrogen. So NLDFT models are available for MOF as well, a complicated process due to their diverse chemistry. So in micromeritics, we provide 30 different types of NLDFT models to match the properties of the material, chemical compositions, pore geometries to understand the pore size distribution and the probe more effectively. So what do we have? Do we need to run extra runs to get to fit for NLDFT? No, you can just use an isotherm, the full isotherm to capture and to use it for the NLDFT modeling. So from here, you are able to use an experimental isotherm. Okay, and with the model isotherms, which is on the kernel, and we have two different methods, either you deconvolute them or you regularize them to get a best estimate of the pore size distributions of the sample. So with the advanced NLDFT modeling, it's able to look even further below, this is for micropore and mesopore size distributions because some samples, it have both micropore and mesopore size as well. So this NLDFT, the advanced NLDFT, it accounts for the fluid-fluid and the fluid-solid interactions. So it accounts for the actual density profile of the absorptive within the pore to treat the fluid as an inhomogeneous. So with that, we also treat the surface heterogeneity in recent NLDFT model, which is the 2D NLDFT model, the latest that we introduced. The model is available for different absorptive gases like nitrogen, carbon dioxide, oxygens, and so on. So NLDFT models are available for selections and easy to fit, whether the deconvolutions or the regulatory. Okay. So when you're seeing here, it also can go further to join two different models together. This is on dual NLDFT, where one of the samples are run,
Recording
run using
stopped.
nitrogen, and another one is running at carbon dioxide and oxygen, and we are able to join two different samples or different analyses together.
Recording in progress.
And the NLDFT is an advanced Ph.D. model. It's able to account for the pore size distributions. So the dual DFT modeling allows user to combine the informations gathered from nitrogen and carbon dioxide isotherm to deliver a full pore size distribution on material, such as carbon slit pores, where the pores of the molecular size are present. The range of the pore size analysis in this method is extended to smaller pore size compared to the standard nitrogen analysis. And in certain samples, we can even go beyond to ultra micropore samples. So those are some of the samples at the ultra micropore. CO2 with a smaller molecules will able to access better compared to nitrogen at cryogenic temperature because of the diffusion limitations. So instead of using nitrogens, we can use CO2 for the ultra micropore samples. So you are able to combine two of these isotope together to further deconvolute and to understand the pore size distribution of the samples. So in micropores, we have a lot of different equipment to measure it, like tree flags, ISAC, and even tree flags and with the different modelings. So feel free to speak to us if you would like to understand more on which instruments best fit for it. So there is a lot of different methods available from here. For example, for the activated carbon, it can be run using a tree flags under argon, and it also can be run with the TriStar with nitrogen and CO2 combined data. So it will be able to help to look into the presence of micropore before you look into a precise measurement of the pore size distributions of in micropore, ultra micropore, and also mesopore region. So in Micromeritics, we are a company that focuses to manufacture instruments, and where our expertise falls are on surface area, porosity, solid density, particle interactions, powder flow, as well as particle size. That's all my sharing today. Thank you very much. Is there any questions?
Okay. Thank you, Ms. Ruby, for your very interesting explanation. Please have a seat here so we can. If anyone here have some question, please just raise your hand. Or maybe the online participants, you can just drop your question in the text message. Okay, Prof. Misri Gozan.
Rise the samples.
Thank you.
Thank you.
Okay, anyone else here? Okay, Prof. Yenny.
Okay, thank you. My name is Yanti. I want to ask about how far the temperature will be affected with we want to measure the BAT, because sometimes if I want to measure the technician ask me how's temperature we can do for your sample. I just worried if it's very sticky or like something like it will be stuck or something in the instrument.
You mean the temperature?
Yeah.
Okay, so it depends because, for example, for an absorptive to take place, it have to have a temperature that is able to create this low pressure environment for the gas to dope on top. So for example, for nitrogen gas, if you are using nitrogen gas as the absorbent, so then the temperature will be at the liquid nitrogen temperature. So if let's say you are using carbon dioxide as an absorbent gas, it can be at 0 degrees Celsius or 273 Kelvin. So for example, if you are using argon as the absorptive gas, there are two types of widely used temperature, 77 Kelvin, which is the liquid nitrogen temperature, or another one is 87 Kelvin, which is using the liquid argon as the cooling medium to create the low temperature environment. At the low temperature or the suitable temperature, that the gas will be able to dope onto the surface.
Okay, so it's mean then will be have distracted our sample. Just dependent of the what is the type of adsorbent we use this. Oh, okay.
Yeah. So it can also have a full list. I do not remember all the lists, but it's available on our website as well on what is the gas and what is the suitable temperatures for different gas. So it's subjected to the absorbate, which is the gas selection, and they will suggest the suitable temperature.
Thank you.
Thank you.
Okay, thank you, Prof. Yanti. Anyone else? So I have one question for you, Miss Ruby. So I just wondering how to choose the suitable gas for the carrier gas. So is it depends on the characteristic, the materials, or depends on the what kind the consideration to choose?
If let's say you synthesize a catalyst and you're expecting it to have be like maybe in mesopore range, I would say nitrogen is a very common and widely used to begin, and it's not that expensive as well. So if let's say you design your catalyst to have mixture of micropore and mesopore, so it can always start the investigation with nitrogen first. Yeah. And later when you change the way to synthesize your catalyst, maybe you can also investigate using another gas to see what is the changes from there, because every gas, the gas molecule size is different, and it will be able to enter even smaller pores as well, maybe, so that it will be better to characterize it. So I would say the investigation would be good to start with nitrogen first, and later on you can also start with different gases, maybe with oxygen, carbon dioxide. Argon is also one of the good choice as well, but depends on whether the availability and also to create the environment for the argon to dope onto the samples is important, because to go to 87 Kelvin using liquid argon is sometimes expensive. So the investigation using argon can also at 77 Kelvin using liquid nitrogen to begin. So you can do some investigations to see whether the micropore or ultra micropore are present.
Okay, because it will be like interesting study to just choose what is the suitable gas for the materials. Okay, unfortunately we have to close this session. So thank you very much, Miss Ruby. And so
Thank you very much, Dr. Kiki. Thank you very much, everyone.
Baca thank you dulu.
Thank you very much, Mrs. Ruby Hui and Dr. Kiki Cornelia Sari Sembiring for the informative session.
Now we may call back Mrs. Ruby Hui and Dr. Kiki Cornelia Sari Sembiring to come to the front stage, and the honor to us to invite the organizing committee, Dr. Deliana Dahnum, to come to the stage to give placard and certificate to our sponsor, PT Era Mitra Perdana.
Ladies and gentlemen, our honorable plenary speakers, moderators, and all of participants who join online. Before we start the next session, it's better for us to take screen capture for our documentation. Please, all of online participants, could you turn on the video?
To our honorable guests, plenary speakers, moderator, sponsorship, and all of participants who join on site, could you please come to the stage to take a picture? Today, we will take a picture together between on-site and online participants. Please, the participant who join on-site, please come to the stage.
Please, for the online participants, please turn on the video.
For all participants who join the symposium on site, please come to the front stage to take the picture. Thank you.
For the online participants, please turn on the video. Kan ituin Pak Hafiz pakai baju ini. Langsung aja. Okay, let's we start from the online participants in slide 1.
Barengan aja call-nya. Okay.
For the slide 1. 1, 2, 3, capture. And for slide 2.
Okay, for on-site participant, 1, 2, 3, cheese. Once more, 1, 2, 3, BRIN. Okay, thank you for on-site participants and online participants who joined this symposium.
Gak apa-apa. Oh, mau gantiin mutu keran.
Ladies and gentlemen, and all distinguished participants, we will start plenary session 3. We have two speakers on this session, Professor Dr. Misri Gozan from University of Indonesia and Dr. Ahmad Ilyas bin Rusdan from University Teknologi Malaysia who joined the symposium online. This plenary session will moderated by Mr. Roni Mariana, Ph.D. from Research Center for Chemistry, BRIN.
Mr. Roni Mariana, Ph.D. is a research professor at National Research and Innovation Agency, BRIN, Indonesia. He got his master's degree from Keio University, Tokyo, Japan, and Ph.D. degree from Tsukuba University, Japan. From 2014 to 2017, he got award from Impact Foundation Scholarship from Master Program and Monbuka Gakusho Japanese Government Scholarship for PhD program. Now he is a researcher at Research Center for Chemistry, National Research and Innovation Agency BRIN. He got many awards and one of them is International Climate Champion Project from British Council.
Well, ladies and gentlemen, we will give time to our moderator, Mr. Roni Mariana, Ph.D. The time is yours.
Thank you Mas Anas dan Mbak Reza. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. The Honorable Head of Research Center for Chemistry, the Honorable all speakers, all professor, and distinguished ladies and gentlemen. My name is Roni Mariana. I will be a moderator for this session. First of all, I would like in online is Dr. Arman that already joined us online from Malaysia. He also will give a lecture for about 30 minutes and then directly to the discussion session. Ladies and gentlemen, because since yesterday there are no pantun delivered, so I would like to deliver pantun in bahasa. Ikan mas dimasak pecak, didapat dari hasil memancing. Every session in the seminar ISAC is always very interesting. Again? Oh, okay, one more. Ke sungai pergi memancing, dapat ikan, dimasak garang asem. Not only very interesting, but the seminar is full of fruitful discussion. Okay, ladies and gentlemen, let's start the session. I would like to invite Professor Misri Gozan. Professor, please welcome to the stage. Silakan. Oh iya, sini. Iya. Before Professor Misri Gozan give a lecture, I would like to to introduce you a brief introduction about him. Professor Gozan graduated from the University of Indonesia, Chemical Engineering, and then master degree from the Technical University, for the master degree he got from the M.Si University, New Zealand. And then doctoral degree from the Technical University, Dresden, Germany. He also finished the postdoctoral program at King Saud University. He has many several work experience. Now he is a lecturer at the Chemical Engineering Department, Faculty of Engineering, University of Indonesia. And he has many research grants since 2017 and until now. So, ladies and gentlemen, let's start this session, and I'll give the time to the Professor Misri Gozan. Professor, the time is yours. Di sana aja.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Thank you, Ibu Prof. Meli, and also distinguished speakers, whether in this room or in Zoom. And thank you, Dr. Roni, for your nice introduction. I would like to be as short as possible to deliver my PowerPoints, my research in sustainability case study of furfural from oil palm byproducts. I come from Department of Chemical Engineering, Universitas Indonesia, and also I just appointed 2 years ago to be the head of the Research Center for Biomass Valorization. It's a multidisciplines of research center in our Faculty of Engineering, but we also try to embrace more researchers from outside, as I would like to introduce in the later slides. Next, okay, so yeah, so sorry. Yeah, we know that policies, there are a lot of policies related to the world trading oils, and those has the contribution to the changes in oil industries. For example, the global edible oil pattern is dominated by palm and soybean oils, but actually before 2004, we know that in the world, soybean oil is the leading edible oil consumption. And after that was overtaken by the palm oil, and especially since 2013, more than 50% of the oil, edible oil consumption is dominated by the palm oil. Palm oil has a lot of advantages. For example, it is a perennial crops. It means that it has a long lifespan. It's not a seasonal crops. The lifespan can have 25 to 30 years. And it's the quick yielding after 3 years after planting, so it has a lot of advantages when we compare to others. And it has a total yield of 4.5 ton, mostly for palm oil, and the rest about 0.5 ton for palm kernel oil or PKO per hectare. If we compare to the soybean, it can be more than 10 times of the soybean. Soybean has only 0.5 or half ton oil per hectares. So, yeah, it is the industry of oil palm is a very huge scale. The economic scale for Indonesia alone is about 20 to 32 billion in US dollar for Indonesia only. And the area is growing, at least 17 million hectares in Indonesia and 6 million hectares in Malaysia. And Indonesia and Malaysia altogether exports more than 85% of the market of the oil consumption, the palm oil in the world. Indonesia about 44%. It's the world biggest palm oil producer, nowadays around 42 billion liters per year. And we introduced in Indonesia and Malaysia, we introduced the Indonesian Sustainable Palm Oil, or ISPO, and Malaysia introduced Sustainable Palm Oil. In the first slides, first couple slides, I would like to talk a little bit about these schemes. Yeah, in the top, I just want to use this opportunity to introduce you to my our books just recently published by Wiley. This is the chemical substitutes of the value-added chemicals. Sorry. Yeah, we have a lot of challenges nowadays. If you see this, if we see this graphs, you can see that the consumption in the oil production, the palm oil production in the left with the orange color, always surpass the need for the consumption, and we see here that there are a lot of differences, but we are now trying to use it more for the consumption in the world. But the trends into 22, especially, we have no picture here. It's becoming bigger. With the export, the gap with the export is becoming bigger. So it means that we have to use a lot for the national demands. So in the future, we have to see at how to. Sorry, we have to see how to develop more products from the produced palm oil. We also have the difficulties that we have a lot of solid waste, and also in the production we have greenhouse gases. So we have to reduce to zero according to international agreement. And we also have a lot of issues about keeping soil quality fertility. I would like to talk more later on about this environmental issue. There are also about land usage alternation and rural area development. I would like to address more about the social issues in the next slides. Yeah, there are a lot of social issues like providing workforce and jobs, and we have to think about product diversification, new income, and other multiplying effect of this industry. Well, there are a lot of hindrances or obstacles in sustainability. For example, several countries have enacted regulations that could become non-tariff barriers to the palm oil trade, and the establishment of the European Union Renewable Energy Directive, or EU RED in 2009. And also the Food Standard Amendment Act by Australia, which shocks our government and our palm oil industries in Indonesia since 2011. Those all declines the CPO export. So these are some major hindrances in the sustainability. Now we go to the environmental issues. I mentioned before, there are some environmental issues. For example, deforestation of tropical rainforests. Some land fires, loss of habitats of rare animals. For example, the orangutan, the Java and Sumatra tiger, and also Sumatra elephant, and also destruction of peatland. We can see here the peatland on the left side of the slide. In the top, there are very beautiful rainforests with the peatland. Wetland and peatland, and which we see on the bottom of the slide and the right side. We see the very ugly look peatland. This is very unfortunate. Those are some environmental issues that we have to cope. We know that there are also some socio-economic issues that we have to encounter. For example, the expansion of oil palm can also result in social conflicts, land conflicts, and marginalization of indigenous people and their livelihoods. And because this all in the beginning, the previous slides I mentioned about there is some barriers in the economics, because this is large economic scale. 85% of world oil palm trade. It's also the economic and issues can also affect the socio-economic issues, become the socio-economics. I mean, it's a typo. The issue of originating in the European Union, if some people thought that it's related to the business competition. But nevertheless, it has very big impact to Indonesia and Malaysia and in terms of oil palm industry. So we have to do something. Then yeah, there are a lot of issues. So Indonesia tried to develop a certification scheme to ensure sustainable cultivation of oil palm and production of palm oil. In 2004, there are this roundtable on sustainable palm oil was founded. Many certified palm oil products are being accepted by international manufacturers, especially companies from the US and Europe. The government of Indonesia introduces the Indonesian Sustainable Palm Oil ISPO certification scheme as a mandatory requirement for all palm oil growers and mills operating. There are a lot of issues that we have been accomplished. We have conducted some. So we have raised some issues, and we success to for the ISPO. For example, the standard development. I don't want to read one by one. I just want to show you, for the reason of time. I just want to mention here that we have tried our best to compare our sustainability in doing the palm oil production, palm oil plantation, and to see whether we have revised the deforestation to this palm oil plantation in terms of gross assimilation and the total respiration. So we see in this picture that we have actually better environmental performances than only letting the rainforest itself. Of course, there are still issues in the animal or rare animal life habitat. So. As a conclusion in this part, I can say that the most important thing is that we have to do something, not only surpassing the ISPO certification scheme, but also we have to do better in terms of economics. Let's discuss about the three things: people, planet, and profits. So first, we discuss about how to convert the biomass to value-added products and bioenergy. So I would like to introduce our case study in our group, Furfural Group. We have some collaboration here, especially with BRIN as well. That my Ph.D. students is working in water residue, wastewater. I don't know what to do at this moment. It's I think the BOD is very low, but still toxic. Of course, because of the HMF and lefulinic acid, of course. But the rest of the solid is very benign because it can be composted easily because they contain a lot of humic acids. I think we can go into the net zero waste into this feature. Thank you.
Thank you, Prof. Misri Gozan. Ladies and gentlemen, the last question come from the Zoom. This is from Augusta, also our college. Professor Misri, thank you very much. It was very interesting presentation. I have question related to the sustainable of biomass supply from oil palm production for Furfural. How to deal if the Furfural demand is increasing? Thank you very much.
Okay, thank you. It's a very nice question. I also asked myself long ago about this. Actually, we calculate how much Indonesia need. Thank you, Pak Agus. Yeah, Augusta. Thank you very much for your question. Actually, I calculated this long ago. Then we realized that even if we replace 100% of the imported Furfural, we only use less than 2% of the solid waste. So we still have a lot to work on. So don't worry, we have a lot of resources, and at the same time, we have a lot of space to increase our production, and at the same time also, we need to work a lot with the rest of the solid waste. So a lot of things that we have to research. So with this, I think your question is answered. But not only that, I would like to motivate that please don't worry and please do a lot of research, because we need to increase the value of the biomass, which means biomass valorization. Thank you.
Thank you, Prof. Misri. Ladies and gentlemen, now we come to the end of the session for Prof. Misri. Let's give a big applause. Thank you, Prof. Misri.
Saya mohon maaf karena tidak bisa meneruskan. Saya harus ada kuliah lagi.
Thank you very much for Professor Dr. Misri for the invitation. Now we will call the professor and of us to invite Professor Dr. Meliana to give a
Card and certificate to our speaker today, and please come to the front stage. Thank you.
Thank you very much, Professor, for the session. Well,
Ladies and gentlemen, we will continue to the plenary session 3 with the speaker from Universiti Teknologi Malaysia with Dr. Ahmad Ilyas bin Rusdan, who joined the symposium online. Okay, for this session, we will give back to the moderator, to Mr. Roni Mariana, Ph.D. The time is yours.
Thank you, Mbak Riza. Ladies and gentlemen, let's continue this session with the lecture from the Dr. Ahmad Ilyas. Dr. Ahmad Ilyas, you already hear me?
Yes, okay, I can hear you.
Assalamualaikum, Dokter.
Waalaikumsalam warahmatullah.
Okay, nice to see you. Before the begin, I would introduce to the audience Dr. Ahmad Ilyas, he got Ph.D. in Biocomposite Technology and Design from the University Putra Malaysia. Now he is a senior lecturer in the Faculty of Chemical and Energy Engineering, University Teknologi Malaysia. He also a fellow of International Association of Advanced Material, Sweden, and many work experience. He got award such as MVP Doctor of Philosophy Gold Medal Award from UPM for the best PhD thesis and top student award. He also award outstanding reviewer by carbohydrate polymer and so on. It is nice to have you here, Dr. Ahmad.
All right, thank you.
Okay, now the time is yours.
But can you see my slide? Okay.
Yes, yes.
All right. Okay. Good. Very good. All right. Okay. Assalamualaikum warahmatullahi wabarakatuh, and very good morning to all of you. So my name is Ahmad Ilyas bin Rushdan, just introduced by the moderator. All right. So thank you for inviting me to give a keynote speech at the 9th International Symposium on the Applied Chemistry in conjunction with the 5th International Conference on the Chemical and Material Engineering. All right. So I'm from the Department of the Chemical Engineering, Faculty of the Chemical and Energy Engineering, Universit Teknologi Malaysia, and then also affiliate with the Center for Advanced Composite Material, CACM, Universit Teknologi Malaysia, Johor Bahru, Johor, Malaysia. So today I would like to present my keynote session on title of nanocellulose reinforced thermoplastic starch preparation, characterization, and applications. Right, before I start, I would like to introduce University Hadiyanto. Maybe some of you have known that we are located in Malaysia, and then UTM, we have a 3 campus, UTM Johor Bahru, UTM Kuala Lumpur, and UTM Pagoh. So UTM Johor Bahru is the main campus, and then UTM Pagoh, we focus more on the agriculture technology. And then we have several faculties, so Faculty of the Chemical Engineering, Mechanical, Electrical, Civil, and Computing. So most of our faculties is engineering. Our bread and butter is engineering. And then we have global present throughout the partnership with many industry, premier industry linkage. Also, as we collaborate with the many international higher education, for example, Oxford, Southampton, and so on. So this is a campus experience in the University Teknologi Malaysia. Alright, so this is my presentation outline for today. So I will start with the introduction, natural fiber, natural resource in Malaysia, properties of natural fibers, nanocellulose isolation and characterization, nanocellulose reinforced starch biopolymer, application of the nanocellulose bio-nanocomposite, and comparing starch biopolymer with the conventional plastic, conclusion and reference. Alright, so most of my materials presentation today is I took from one of the book just published in a Die Groente, Berlin, Germany in 2023, just a month ago. Nanocellulose reinforced thermoplastic starch. So edited by me, Prof. Sapuan, and Dr. Muhammad Faiz Nur Rahim. Alright, so this is based on the Scopus data. So I'm the top author in the topic of nanocellulose after the Rogers Orlando. And then for the introduction, so start with why we are using starch bioplastic. So due to the plastic industry, they're using petroleum-based synthetic polymer. Alright, so as formulation use 9 billion plastic bags per year, and we are the most one of the country that using plastic bag. most plastic bag. Malaysia, this one is according to the Malaysian Plastic Manufacturer Association, MPMA. So we have a lot mountain of the plastic. And then problem encountered with this non-biodegradable plastic is it's a non-degradable and takes almost to 300 years to degrade. And then besides the source of this material also is a non-renewable nature using the petroleum-based plastic. Alright, so this is a turtle. They show the turtle in which they consume jellyfish, but they think that the plastic bag is the jellyfish. So they will cause strict to the turtle. Okay, so biopolymer manufacturing, starch is one of the best option due to its easy availability, biodegradability, and renewability. So we have others biopolymer, for example, the PHB, polylactic acid, chitosan, and so on. However, starch is one of the options. Although in some of the experiments, we will blend starch with the polylactic acid, PHB, to get to increase the mechanical properties. Alright, so the starch, however, the starch-based films for packaging have been reported to have a low water barrier resistance and poor mechanical strength. So usually when we want to carry goods or we want to keep a goods for a long time, so we must have a very good water barrier resistance and mechanical strength. Otherwise, we have a problem to carry the foods, and also as well as we have a problem to keep the food. Alright, so the addition of the nanocellulose fiber during the preparation of the starch composite film is an effective way, one of the effective way for further improving the functional properties of the packaging film. So this figure shows the incorporation of the natural fiber within the starch solution, so that we can get a biocomposite film with the high mechanical properties. So the green nanocomposite film are predicted as a next generation packaging materials. So before we move on to the nanocellulose, so we have to know what is the natural fiber. Alright, so natural fiber which grow or develop and come from the natural resource like plants, animal, and mineral fiber. So from here, from the diagram, we can see that the natural fiber we can divide it into two: organic fiber and non-organic fiber. So for non-organic fiber, can be classified into mineral fiber, and then can be categorized as a M.Si, crocodilite, tremolites, actinolites, anthrophyllites, and crystolite. Alright, so for this presentation, I would like to focus more on the organic fiber, which is a lignocellulosic fiber or plant fiber. Alright, so plant fiber we can categorize into two: wood fiber and non-wood fiber. So due to the problem of deforestation, so we want to reduce the deforestation, we use non-wood fiber, in which this non-wood fiber actually most of them is left over from the product. For example, the rice straw, alright, rice stalk, and then the sugar palm fiber and the roselle fiber. So this is the residue, agricultural residue. Alright, so within the non-wood fiber, okay, so we can be categorized into 6, which is the leaf fiber, bast fiber, fruits fiber, stalk fiber, grass fiber. Alright. Okay, these are some of the natural resource in Malaysia. For example, the sugar palm. Okay, we also have in Malaysia, and this is a distribution of the sugar palm. So you can see throughout the Southeast Asia country, and then we have indicate that there are many industry in the Sumatra. I think they're working on the sugar palm fiber. Alright, and then the coconut fiber, cocoa bean also. We have several in Malaysia, Indonesia, and then the betel nut, and then the sugar cane. Alright, so we left with the bagas, and then this bagas can be used to be reinforced with the starch, and then the banana stem, pineapple. Alright, in Malaysia we have many in Johor, with the southern part of Peninsula Malaysia. And then oil palm production, as we know that Malaysia, Indonesia, we have a lot of oil palm. And then roselle, okay, a rice straw, right, rice straw, I think they do China, India, all right, Indonesia. We have a lot of rice straw. And then these are some of the properties of the natural fiber. So before we want to extract the nanocellulose, we have to know what is the chemical composition, especially for the cellulose. So what is the content of the cellulose within the fiber. Alright, so each fiber, they have a different chemical composition. If you look at the sugar palm, they have a cellulose content about 40 to 66%. And then if you look at the oil palm, alright, they have a lower cellulose content compared to the sugar palm. And then if you look at the pineapple leaf, alright, pineapple leaf, they have high cellulose content, which is up to 81%. And then within the fiber also, for example, this one, sugar palm fiber, we can see that the sugar palm frond, they have a high cellulose content, which is 66%. Alright, so why is it very important? Because the yield of the nanocellulose is much depend on the cellulose content. Okay, natural fiber reinforced thermoplastic starch. Alright, so this is a preparation of the natural fiber reinforced starch biopolymer. So from the starch, we put into the distilled water, and then we add some of the plasticizer, for example, the fructose, glycerol, and sorbitol. And then with several loading, okay, with a different loading, and then after that we will mix and heating at 85 degrees Celsius to make the starch plasticize, okay, turn shape, and about 20 minutes. And then after that, during the preparation of the starch, we can include natural fiber, all right, as a reinforcer. And then we can casting the plasticized solution into the plating disc, and then we can peel out, and then we can do a characterization. Alright, so this one is a different with the blowing technique. So usually in the conventional plastic industry, they're using a blowing for high productive plastic. So this one we already published in the polymers. And then these are some of the example that been used by the many researchers that reinforce natural fiber with the different types of starch. For example, this one is a bagas fiber reinforced with a cornstarch. And then at a different loading, all right, they get the high mechanical properties, which up to 4 megapascal. And then hemp reinforced cornstarch, bagas fiber reinforced cassava starch, and then a loofah fiber reinforced cassava starch composite. And then if you can look at the elongation, all right, so the elongation is decreasing as we increase the loading of the natural fiber, right? All right, so why nanocellulose? All right, so nanocellulose has a nanostructure of 1 to 100 nanometer in diameter and 10 to 100 of nanometer in length. Okay, so this is illustration of the hierarchical structure of the cellulose and the schematic illustration of the crystallite and amorphous region in the cellulose fiber. So from the tree, we can extract the fiber. Alright, from the fiber, we can extract the cellulose. And then, as we know that the fiber, they contain three main components, which is the cellulose, hemicellulose, and lignin. Alright, so different fiber, they have a different chemical composition, as I showed in the previous slide. Alright, so from the cellulose, alright, the cellulose, they have amorphous region and the crystalline region, and then we can use a different techniques, whether we can use a chemical technique, mechanical treatment, or the combination or hybrid of chemical and mechanical, or we can use the enzymatical and so on. Alright, if you use the acid hydrolysis, we can produce the cellulose nanocrystal, and then if you use the mechanical treatment, in which only they make a defibrillation of the fiber, we can produce the cellulose nanofiber. So this is the chemical composition, chemical structure of the cellulose. And then this is the illustration of the component of the lignocellulosic. So you see the cellulose in the black, color, and then the lignin in the blue color, and hemicellulose. So in order for us to isolate the cellulose, so we can use the several treatment, a chemical, enzymatical, biological, and physical treatment. And then for the chemical treatment, for example, we can use the cellulose isolation. This one is done in 2017. Lignin were removed by the sodium chloride, and then the hemicellulose can be removed by using the sodium hydroxide. And then there are several pre-treatment also can be used. For example, you can use iodide liquid, which is more sustainable. Means that you can recycle the solution back, and they can be reused again. So this one we already published in, they just published in 2023. I think end of this year, International Journal of the Biological Macromolecules. And after that, after we get the cellulose, all right, we can convert cellulose into cellulose nanofiber, which is a nanocrystalline or the nanofibrated cellulose using the chemical and mechanical treatment. For example, the acid hydrolysis, high pressure homogenization, ultrasonification, microfluidization, grinding, and crushing. So we update our work in the 2023, just published in the International Journal of the Biological Macromolecules. Alright, so what the nanocellulose can be divided into three categories, which are bacterial nanocellulose, nanofibrated cellulose, and a nanocrystalline cellulose. So what is the difference between these three types of the cellulose is the crystallinity. Alright, so if you look at the crystallinity of the nanocrystalline cellulose, it's a high crystallinity, which is about 90% compared to the bacterial and nanofibrated cellulose. So this is due to the degradation of the amorphous region, which it left the crystal part. Okay, so for surface area also, the nanocrystalline they have the high surface area compared to the other nanocellulose. And then if you look at the size, alright, the size of the nanocrystalline is quite low, okay, short. The size of the fiber is short compared to the nanofibrated, which is up to 10 micrometer, and the bacterial cellulose is up to 1 to 5 micrometer. So you can imagine the size of the shape of the nanofibrated is like a noodle light, and the nanocrystalline is like a rice light. And then nanocrystalline, so this is an image of the nanocrystalline. So under the electron microscopy, and we can see that the diameter of the nanocrystalline is 9 nanometer. Right. So this one is another nanocellulose, which is the type is a nanofibrated cellulose, isolated from the sugar palm fiber. So we can see that it's like a thread light or the spaghetti light, in which the diameter of the cellulose of the nanocellulose is 5.5 nanometer with the length of up to 1 micrometer. So this is a bacterial nanocellulose. So this one published by Prof. Abran, Journal of Material Research and Technology. So this is the sum of the properties why we are using a nanocellulose instead of other nanoparticle or nanofiber. So it has a high surface area, it's a high aspect ratio, high crystallinity up to 90%. And then has a low density, it's a biodegradability, it's renewable and available. High tensile strength up to 7.5 gigapascal, high mechanical strength, Young modulus up to 150 gigapascal, and it can be produced from a various type of plants. As long as one of the journal they say that the optimum range of the cellulose that can be extracted from the plant is the make sure that is about 28%. Otherwise, it will cost you a lot of materials. And then high thermal stability up to 350 degrees Celsius means that if you insert in the polymer that have the processing melting point of below than 350, so it can be used. So higher than that, maybe you have to change other nanofiller. So it's a abundant surface of the hydroxyl group, OH group, and then so what is very important because it can be modified and then compatible to be reinforced with the polymer, for example, starch. And then so this is one of the case study that we use the current utilization of the sugar palm tree in Malaysia. Alright, so this is a sugar palm tree. Alright, Indonesia also have. Okay, so the sugar palm plantation in Indonesia is about 809 hectare, which located in the Tawau, Sabah. So the sugar palm tree can yield up to 50 to 100 kg of starch. So the main product actually is a kolang kaling, or the sugar palm rock, atau aren. In Indonesia, they call it pokok aren. So after they have been harvest for several years, so then the tree will left to die or burn out. So from here we use the tree to extract the sugar palm, and then from the sugar palm we extract the cellulose. From the cellulose we convert into the nanocrystalline and nanofibrated cellulose. And then so these are morphological properties of the cellulose after treatment, in which the fiber were decreasing, the diameter of the fiber decreasing due to the chemical treatment. And then we can see that the increment of the crystallinity up from the 55.8% to 85.9%. So this one, after we look at the using the FESM and the FESM and XRD for the crystallinity. So all work has been published. And then, so this one is a nanofibrated cellulose. Alright. So from here we can see that the crystallinity is lower compared to the nanocrystalline cellulose. Alright. So because in the nanofibrated cellulose, they still have the amorphous region within the nanofiber. However, you can see that the diameter decreasing from 212 to 5.5 nanometer. So we also have done works on other types of natural fiber. For example, the ginger. Alright, for the ginger, we turn into ginger nanofiber. Alright, ginger nanocellulose, and then some of the fiber actually they have their own properties. For example, this one, ginger. Alright, they have anti-microbe properties. Means that if we reinforce with the polymer, so it will give the effect of the anti-microbe. So we don't have to use maybe essential oil or the silver nanoparticle or metal nanoparticle as the anti-microbe agent. And then we also have done research on the water hyacinth, kenaf, sugarcane bagas, agave gigante, and then Coloscale. So this is one of the Coloscale esculente, and then rosin. Alright, so this is a process of how the nanocellulose be reinforced with the starch. Alright, so this is a clear film. Alright, so there is an effect of the reinforcement of the nanocellulose within the starch biopolymer, in which from here we can see that the tensile mechanical were increasing up to 11.47, 2 times increment of the tensile. Right, so this one we only include 0.5 loading. Alright, so it can increase up to 11.47. So this is due to the bonding that made from the nanocellulose with the starch. And then the elongation also were increasing. So usually the elongation were decreasing, but this one the elongation were increasing. And then the water barrier were resistant, water resistant to the film. And then in terms of the nanocellulose function as the physical barrier structure based on the tortuous theory, means that it acts as the barrier. Alright, so they prevent the movement of the oxygen gas molecule through the barrier. Alright, so we started the experiment from the 2012 until 2018. Alright, okay, so from here we can see that the tensile strength were increasing as we include the fiber. Alright, so for example, this one, sugar palm cellulose were reinforced with the sugar palm starch, increasing up to 10.5. However, this one they use a 30% loading. Alright, in 2018, I'm using the only 0.5. Alright, 0.5 weight, and then it much better compared to the loading of the cellulose. So this is due to the size of the fiber that affect the interaction of the fiber with the starch. Okay, these are some of the experiment. Alright, so we have done several experiments and we published in the Journal of the Natural Fiber. It's a Q1 journal, and then we can see that the tensile strength of the mechanical properties especially for the tensile strength, were increasing after we add several loading of the fiber. However, at some point, it will decreasing due to the agglomeration of fiber, in which it will not give the better interfacial bond between the starch and fiber. Alright, so all this is our colleague from Hiresh, from our laboratory, Jumaidin, Jafar, and Abran. And then this one is on the using a durian, durian fiber reinforced with the TPS V-wax mixture, so we get some rigid structure of the composite. Instead of if we're using only the starch, it will give us a film, right? So from here we can see that the fiber content, when we mix with the durian fiber with the thermoplastic cassava starch and the beeswax, we can see that fiber loading is maximum up to 40 degrees Celsius, and after that it will drop due to the agglomeration. So this one also same as the flagellar strength. So this one we publish in the International Journal of Biological Macromolecules. And then another study that been done on the pandanus, because pokok pandan we have a lot in Malaysia and Indonesia, and then we make into the we mold it, and then we make into the rigid structure. And then we can see that the different with the durian is 40%. For however the power pandan is a 50% loading, and then we drop after 60%. And then another study, and we using the black seed, alright, Habatu Sauda, will be published, just published this couple of weeks. Fibers we published in the Fiber and Polymer, this QQ1 journal. So this one we using the Habatu Sauda reinforced with the corn starch, and then we can see the increment banana nanofiber reinforced with the banana peel starch, and then we can see that the tensile were increasing up to 5%, and then it decrease after 7%. Alright, so there's a various study. I think there's a tremendous study have been done on the reinforcement of the natural fiber with the starch, and then we are one of the team that working on it. Alright, so you can see that there's a lot of study. They're using eucalyptus, rice nanoparticle, nanocellulose, and then this is our work, sugar palm, bamboo, sisal, and so on. So this is the application of the nanocellulose bio-nanocomposite. So it can be used as a film, and transparent Ginger nanofiber film. And then we also done on the, because for the 100% starch, it can be in the rigid structure. Alright, so we want to mold it into several shapes. So we have to reinforce with the thermoplastic, for example, polylactic acid, and then we also blend it with the wax, alright, and so on. Okay, so because of the starch, we have a problem with the antimicrobial effect, in which the starch is not an antimicrobe, and then it easily be attacked by the microbe. And so in order for us to overcome the problem is we reinforce, we add the cinnamon oil, will give the antimicrobe properties to the film. And then we also work on the using the nanosilver, to make the starch antimicrobe. And then if you comparing the starch biopolymer with the conventional plastic, so this one is a starch, and then this one is the LDPE, alright. So if you look at the tensile mechanical is up to equivalent to 10 to 30, and then the tensile strength for the LDPE is a 10 to 20. However, the elongation at break still can be comparable, alright, but starch need to be modified, means that we have to put the optimum plasticizer. And then for the young modulus also is comparable, and then however for the water vapor permeability, alright, so this one because starch is hydrophobic, materials, all right, biopolymer. So we need to, maybe you need to do some modification or a grafting or radiation to make the starch maybe have a, some of the structure is the hydrophobic, or we can do a coating. And then in terms of the cost, all right, the cost of the LDPE is much lower, much higher compared to the starch. But in terms of the starting for the installment of the equipment for the starch bioplastic is higher, the method of the technology. But in terms of the raw material cost, so nanocellulose reinforced starch is abundant and affordable. So the cost may vary depending on the source and the extraction methods of the starch and nanocellulose. However, for the conventional plastic, so it derived from the petrochemical feedstock. So it's subject to the fluctuation in the crude oil price. Right? So sometimes it may high, sometimes it may low. And then the processing cost involve the specialized equipment and techniques to properly disperse and incorporate to the nanocellulose. All right. And then in terms of the conventional plastic, is well established and the environmental can be efficient due to the maturity of the industry because we have been using it for more than 50 years. And environmental regulation and the needs for the specialized recycling facility might increase the cost. So this is our problem actually, in which in terms of the environment. So some of the method being used is to reduce the use of the petroleum base. Some of the we change into the bioplastic. Some of the method is we try to recycle. Alright. And then in terms of the manufacturing and scale, so initial cost might be higher. So due to the R&D effort, okay. So it's not mature yet because we still try and error in terms of the material itself and then the processing. So how to make it into commercialized product. And then it's a mature and highly optimized economic of kit scale and efficient mass production. And environment consideration, so environmental friendly, okay, for the bioplastic, it's a biodegradable material. For the conventional plastic, is a plastic pollution and environmental concern lead to the regulation change tax fees related to the plastic use and waste management. So as in conclusion, so the reinforcement of the natural fiber, the nanocellulose with a starch-based biopolymer yield a high mechanical and thermal properties for the specific application. So it's a potential ecological impact, scalability of the production and overall material performance. Alright, so this is a list of the reference that we used presentation. So this is a recent book publication, and then our team have published books. So this is a new book, and then additive manufacturing for the biocomposite and synthetic composite 2023, and fiber reinforced polymer composite published in the MDPI Basel, Switzerland. And then this is also a recent book published 2 months ago on the nanocellular reinforced thermoplastic starch published in Berlin. And then another book just published 2 months ago, synthetic polymer composite properties and application. Of our team also working on the pulping and the paper making of the non-wood plant fibers. So also this one for intention to replace the conventional petroleum-based plastic. Alright. So by using a non-wood, although the non-wood have been actually it's been saturated technology. But however, due to the modification, we can still working on the modification of the cellulose fiber or the non-wood fiber in order for us to work with the many types of application, for example, electronic, food packaging, or maybe active food packaging, and so on. And then this is some of the books published in NDPI under special issue. And then mineral field polymer composite. And then aerospace, because when you're working with the polymer composite, so we're working on the fundamental material, and then that material is potential to be used in various applications. And then industrial application of the nanocellulose and its nanocomposite published last year in SCB Cambridge, US. And then we also work on the safety and health in composite industry because we're only not working on the natural fiber, we're also working on the synthetic fiber, for example, the glass fiber, carbon fiber. So by using this type of fiber will give us safety issue. So we have to comply with the regulation. And then the rosin, all right, we made one book on the rosin, published in Cambridge, LCV Cambridge. And then this is a bio-based packaging. So within this book, we cover on the various types of the materials that have been used for the food packaging. For example, the chitosan, polylactic acid, PHB, PBS, PBAT, okay, and then starch also, cellulose, and so on. And then biomedical, and then automotive. So this book, pokok enam, the special book, we publish with the UPM Press on the pokok enam, alright, atau dipanggil in Indonesia pokok aren. Okay, some of the product also we shows that be already been developed by the Indonesian. And then for further information, so you can contact me at ahmadilyas@utm.my. Alright, okay, thank you very much. So sorry for taking too long time to present my materials.
Okay, thank you, Dr. Ahmad Ilyas, thank you for the nice and comprehensive presentation. Now we will open discussion. Please, in the forum, is there any question? Raise your hand and okay, silakan. Bu Liz.
Thank you. My name is Ibu Liz. I have two questions. First is, I want to know about the method how to make the composite. And the second question, have you produced the composite in industrial scale? Yes. Thank you. Only two questions.
Alright, okay. Alright, thank you very much. Okay, for the first question, how do we produce composite, right? Alright, so for the composite, there are many methods you can produce a composite. For me, to produce the starch-based biopolymer, I'm using the solution casting. Alright, solution casting method. And for the slides, I also show that we can produce the biocomposite internal mixer, or you can using the extruder.
Just research.
Okay, is it answer your question?
Have this product has produced by industry?
Alright, okay. So actually, before I joined UTM, so in which we produce what we call the frame from the Knaf biocomposite. Alright, so that one is under Universiti Putra Malaysia. So I'm one of the member for the project. And then so we have produced, and then we also have a collaboration with the Proton to produce the composite to make into the one of the road, or we call it one of the road, anti-robber road. Anti-robber road. Okay, so that one still in the experiment. Alright, so we have produced, but most of our experiment is still in the lab. Means that, for example, the starch bioplastic. Alright, so although we have produced this into the pilot plant, right? We collaborate with the Universiti Putra Malaysia and several university. Okay, so to produce the bioplastic from the starch, PLA, and some of the plasticizer. All right. So this one is still in the pilot plant due to the processing issue. Right. But still, there is still opportunity for us to develop the method. However, I also collaborate with one of the researcher in Brazil. So they also have an issue in producing a biodegradable starch film in a way of using the solution casting. All right. So there's still problem in processing. Blowing method in which you blend PLA, starch, and other several plasticizers to still can produce film.
Thank you.
Okay. Your question?
Thank you, Ibu Liz and Dr. Ahmad. Is there any question? Maybe one more question? Yes, please. Oh, okay. Please. Maybe short question.
All right.
Thank you for the opportunity. Thank you for the interesting presentation. I would like to
All right.
ask about synthesis of the bioplastic based on the starch and PLA. Do you use a compatibilizer? As we know that the starch is hydrophilic and then the PLA is hydrophobic. Do you use a compatibilizer to increase the compatibility both of the material? And what is your opinion? How important of the using compatibilizer in produce of composite? Thank you.
All right. Okay. All right. Thank you very much. Okay. Actually, for our study, okay. So we already done one experiment, several experiment on the starch with the PLA, and then we only use the plasticizer. All right. Using a plasticizer. But yes, compatibilizer is very important because you want to bond between the hydrophilic material and the hydrophobic material. And then so I saw also some of the experiment that be done by other researchers. They're using the compatibilizer because yes, you can. It's very good to use a compatibilizer, but for our team, all right, we use only plasticizer. All right, and then in terms of the what we call it, the I think that's all. Kita masuk pula. Alright. Okay. So for us, we using a plasticizer, but some of our friends also they modified the starch. Alright. Means that they modified the starch and then after that they reinforce with the hydrophobic polymers. For example, the PLA, PHB, and PP, and so on. Alright. So there are several methods whether you want to use the compatibilizer, it add into the composition of the starch and PLA, or you modify the starch and then you combine with the PLA or other hydrophobic polymers.
Okay, thank you. Because of the time limited, is there any question? Maybe can directly email to the Professor Ahmad. Sorry, Mr. Ghazali, because already time is up. So let us give applause to the Dr. Ahmad Ilyas.
Thank you very much.
Thank you, Doctor. I give time back to the MC.
Thank you. Thank you very much to our speaker, Dr. Ahmad Ilyas bin Rusdan, and our moderator for the informative session. Thank you for your attendance and participation in the plenary session 3. For Dr. Ahmad Ilyas bin Rusdan, we will give you certificate online and here the certificate of plenary session. Thank you.
All right, thank you.
Well, ladies and gentlemen and distinguished participants, now we have 10 minutes for a coffee break and we will continue to the plenary session 4 at 10:35. You may bring the meal and the mineral water into this room, but we are sorry for coffee, tea, and meal. It's not allowed to bring to the room. Please enjoy the meal and thank you.
I changed several projects from cellulose focused on organic chemistry, sometimes cellulose focused on chemical engineering, and sometimes focused on polymer chemistry, and sometimes microbiology. So I don't know much about this subject, but I know a little bit about each subject. Most of my research focus on how can we get the cellulose by cheaper. So I focus on the making of products to paper industry. And after that, I focus on biomass to make the glucose the cheaper way. And nowadays, I make the cellulose to plastic replacement or other things by the cellulose nanofiber. So today, I'll speak about the most focus on cellulose nanofiber. Yes, the biomass are composed by the cellulose is composed by the glucose. And also focus on morphology of the nanocellulose. So we usually check the morphology of the nanocellulose by the TEM, but it spent the time. So we try to easy measurement of the morphology of the CNF by the nanoparticle size analyzer or different based on centrifuge. We call those things water retention value. Yeah, we use very high centrifuge process, and how much of the water keeping, it depends on the morphology of the nanocellulose. Yeah, there are too many raw materials for nanofibrillation. Yeah, we can use every available materials, but most cheap ones are from the chemical pulp. They are industrial scale, and they can make very cheap cellulose raw materials. But sometimes I focus on the cosmetic raw material. If I focus on the cosmetic raw material, in cosmetic industry, they don't like the wood. They like some specific raw material. So if some kind of the specific raw material containing the cellulose, we can convert those raw material to nanofibrillation or nanoparticles. So these days, we focus on every different kind of the raw material. Last week, we get the rose flower leaf. No, rose flower itself, rose. So we can make those things to nanofibril, ongoing. Or one of my graduate students tried to make the red ginseng making process. They make after extract the red ginseng component, they make some kind of the residue. So we can try to make those residue to nanofibril. So we can make those components to sell the cosmetic company. In our labs, focus on making the pre-treatment steps. We usually use the carboxymethylation substitution reaction or tempo oxidation reaction. In cellulose chemistry, tempo oxidations are very specific oxidation method because they only oxidize the primary alcohol. In glucose, there are 1 primary alcohol and 2 secondary alcohol. If they oxidize secondary alcohol, we need too much of the oxidant. But in tempo oxidation, they only oxidize the primary alcohol, so you can control the carboxylate content with a very limited amount of the expense in chemicals. So pre-treatment to carboxymethylation or tempo oxidation, we can go to the mechanical nanofibrillation by high pressure homogenizer or supermass collider. Usually we call those things to grinder. These things are the method of the carboxymethylation. For carboxymethylation pre-treatment, first steps are we should make the cellulose to anion. Making cellulose to anions are first we put the sodium hydroxide in the ethanol, so make the sodium ethoxide solution. And sodium ethoxide solution react with the cellulose, we can make the cellulose to anion. And after that, we make the cellulose to anion, we can make the chemical reaction with the monochloroacetic acid. Monochloroacetic acid main body, and cellulose nanofibrils are new nucleophile and in SN2 reaction. So we can make the carboxymethyl cellulose, but our targets are not carboxymethyl cellulose. Our targets are carboxymethylated cellulose to nanofibril. Those reactions come from the carboxymethyl cellulose, but our targets are not carboxymethyl cellulose. Carboxymethyl pre-treated cellulose nanofibril. By proton NMR, we can calculate the degree of the substitution and which location of the O2 position or O3 position or O6 positions, position of the substitution can, we can find out by the proton NMR anomalic peak hydrogen analysis. Yeah, these reactions are tempo oxidation. Yeah. With the tempo radical, we can put the sodium bromide and sodium chloride. Yeah, we can, those things go to the catalytic reaction, change the primary alcohol in cellulose to aldehyde, and finally they change to carboxylate. So we can control the degree of oxidation by amount of the oxidant. So after the reaction, we can check out the carboxylate in anomalic peak, and so we can calculate the degree of oxidation. Yeah, these things are the machines for nanocellulose making. So I have the pilot scale of the supermass collider and high pressure homogenizer in my company. So I can use those things to my research. So we can make very large scale, pilot scale of the cellulose nanofibril by different methods. Yeah, one time I worked with the Korea Ceramic Research Institute. They focus on the extract the silica from the rice hull. Yeah, after extract the silica from rice hull, they ask me make these rice hull based things to cellulose nanofibril. So I go to different kind of the carboxymetal substitution reaction and make the nanofibril by grinding and high pressure homogenizer. After that, I measure the viscosity difference. This cellulose nanofibrils have the very high secondary interaction between cellulose fiber to cellulose fiber and cellulose fiber to solvent water system. So in very low shear strain, they have very high viscosity. So they cannot measure the conventional viscosity method like the Brookfield method, or when you apply the Brookfield method, they only turn on the middle of the section. They cannot turn. So usually we should measure by the rheolometer. So in my lab, we have the rheolometer and measure this viscosity of the making the nanocell. So after with different carboxymethylation and different combination of the nanofibrillation, we can get the different viscosity of the materials. Yeah, this with the DS.3 and DS.4 means we learn different kind of the pre-treatment, carboxymethylation degree of substitution 0.3 and degree of substitution 0.4. Most of the research on the carboxymethyl pre-treatment method are focused on DS.1. In other research groups are DS.1, and commercial carboxymethyl cellulose are focused on DS6 to DS2.0. Because less than DS.6, very difficult to make the fibrillation by the blender or low mechanical treatment. So my research groups are focused on between DS.2 0.6. There are very different kind of the rheological property and mechanical property come from these things. Other research group from DS.1, they report increase the DS means decrease the size of nanofibril and increase the viscosity means increase the DS. But based on our research group, this viscosity go up and down at around the DS.5 or 0.4. It's depending on the amount of the mechanical treatment. These things are rheological property come from the different mode of the measurement of the rheology. In here, there are two terms, storage modulus and loss modulus. In Gale structure, storage modulus means it's like the solid-like force. Yeah, solid-like. And loss modulus means it's like the liquid-like property. So in very small amount of shear stress, they have very high solid-like property. But when you push the high strain area, they change to solid-like structure to liquid-like structure after the yielding point. So based on this property, we try to make some kind of the thermal filler. These cellulose nanofibrils are a lot better thermal filler property than commercial hyaluronate or some Italian company try to make thermal filler from the carboxymethyl cellulose. In hyaluronate-based thermal filler, they try to make better property by cross-linking. So they put the cross-linking chemicals. Thermal filler from hyaluronate, most of the problems come from the residual cross-linking agent. If this cellulose nanofibril have a lot better thermal filler property, we don't need to put the cross-linking agent. So depending on the degree of substitution and depending on the number of paths of the grinding or high pressure homogenizer, we can control all the different rheological properties. We make the 3 paths of high pressure homogenizer, 6 paths of high pressure homogenizer, and 9 paths of the high pressure homogenizer and compare the property. So in high degree of substitution, too much mechanical treatment means they decrease the viscosity and decrease the Gale properties. Oh, sorry, I put the wrong direction. These things, we measure the zeta potential and amount of the chemical treatment. We try to make more carboxylate, means they increase the negative anion. So we measure this chemical treatment by proton NMR or zeta potential, or sometimes next we'll try to titrate those things. Okay, that was wrong.
Recording in progress.
we increase the cations, they increase the Gale strength. But divalent cation come from the calcium. They increase the Gale strength up to optimal condition. When we put too much of the divalent cation, they start to decrease the Gale strength. So if we control the amount of the cations, we can make a lot stronger gels, like the sodium alginate. Yeah, those things we try to make the temper oxidized cellulose nanofibril with different amount of the oxidant. We usually use the NaClO, sodium hypochlorite, and those amount of the sodium oxidant means with the different level of the oxidation means we have the different amount of the carboxylate. So they, in small amount of the low charge of the oxidant and high charge of the oxidant have the different Gale strength. In this calcium cation, we can see the decrease of the Gale strength after the optimum condition. Also, we try to make the nanofibrillate from many different raw material. One time, one company from the Apple, they make the apple juice. Making apple juice process, they make a lot of the apple skins. So if they make this apple skin to nanomaterial, they try to make this apple skin-based cosmetic product. So we try make these things with the nanomaterials. Apple have the own carboxylate. Apple skin have the pectin compound. Pectin compound have a high amount of the galacturonic acid. But with those galacturonic acid, it's not enough for the nanofibrillation. So we put extra carboxylate by the carboxymethyl reactions. So those things are the opposite. So with more substitution reaction, they get the more anions. Those things are, the left things are the amount of the carboxylate, and right things are after the make the nanofibril, how much of water they holding amount. So with the introduction of the carboxymethyl, they improve the water holding ability. So we can use these things to the in cosmetic humectant things. Also, in cosmetic, we use the rheology modifier. We control the drying touch. So most of the case, they put the carbomols as the rheology modifier, and we check up what's their viscous property. Without the chemical treatment, they have very low viscosity. They increase the carboxymethylation, they improve the viscosity property. But after the DS.2 get the maximum viscosity, and when DS.4, they start to decrease the viscosity. In apple skin, they have the own carboxymethyl group come from, not carboxylate, they have the own carboxylate group come from the pectin compound. So they don't need too much of the chemical treatment as the pulp or other kind of the cellulose. This one's the different cultivar of the apple with the things, and one of the apple cultivar, Busa, have a very high gel strength property, but Gamhong cultivar have very low gel strength property. So if we use the Busa cultivar, we can get the very nice cosmetic rheology modifier things. Yeah, these things are, when we make the emulsion, cellulose nanofibrils are working as the networking structure. That's improve the emulsion dispersing property. So, we try to make the oil and water emulsion and put the extra amount of the cellulose nanofibril and put together by homogenization and check up the emulsion stability things. So, putting the cellulose nanofibril improve the emulsion stability a lot. So, in cosmetic process, if we put the extra amount of the cellulose nanofibril, that can make the prevent the phase separation of the oil phase and water phase. Also, these things are, when we make the emulsion, with putting cellulose nanofibril, decrease the emulsion size. So we make one time with we make the cosmetic things with putting the cellulose nanofibril. So they decrease the emulsion size and improve the cosmetic property. The luminizer things are the measurement of the emulsion stability. Next, one of the Korean company is well known. I forgot the name. One of the Korean cosmetic brand, they focus on the Jeju Island tea. So they ask us, they make the cosmetic things from the tea leaf and they make a lot of the tea residuals. So we try to make the tea residuals to nanoparticles. So in monosaccharide analysis, there are many cellulose and pectin things. So with this raw material, it's not go well, cellulose nanofibrillation. So we put some extra carboxymethyl pretreatment. So increase the zeta potential and carboxymethyl pretreated cellulose nanofiber increase the water holding ability and also viscosity things. So we can use this T residual material for cosmetic humectant or rheology modifiers. So instead of the glycerol or carbomer, we can put those cellulose green tea residual cellulose nanofibers. We also measure the Gale strength as the storage modulus and loss modulus. Without the chemical pretreatment, we can get the not Gale-like, just the watery materials. With the carboxymethyl pretreatment, we can get the Gale strength, and so with the carboxymethylation DS.3 and DS.4 can get the strong Gale property. I'll skip these things. Okay, this is my university. It's middle of the South Korea, called Cheongju, and I have been 3 graduate students from the Indonesia. 1 already graduate and 2 graduate students are sitting in the middle. Okay, thank you for coming to my presentation.
Thank you, Prof. Shin, for the interesting presentation. If you have any question, please wait. We will have the question answer discussion at the end of this presentation. For the next presenter, we have Dr. Sudaryanto. I will do a short biography of Dr. Sudaryanto. So Dr. Sudaryanto is is a research professor at research for advanced material of BRIN. He received his bachelor, master, and PhD from Kobe University, and he has several publication patents related to his expertise, which is polymer material, especially for battery application. Without further ado, I please welcome Dr. Sudianto.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Thank you to the committee to give me chance here. It is honorable for me to have a chance to talk about my recent study related to battery material. But I'm sorry, maybe I cannot give you, set of view, but I hope what I will talk here can give you some inspire how to, how to study what is the problem in the battery material and so on. Okay. My presentation title is the how to enhance the electrochemical performance of high voltage battery material based on nickel and mangan by using the mixed electrolytes. Okay, next. Oh, that I should do by myself. Sorry. So, okay, I think all of us know that in our daily life, we cannot, we are very dependent on the battery, is either for electric vehicle, oh sorry, it's, okay. Especially and recently for electric vehicle and also for energy storage and other application in our daily life, we always need battery. And nowadays, among the battery, the most battery who has the high energy density is a lithium ion battery. In the application, we always ask to request a battery. This is the So the battery sometimes requested to be have high power or having the specific energy to have the low cost, the lifespan, of course, lifetime, and also safety and other performance. So if we see this requirement, almost the key technology is on the material. I can show you here that if we look at the cost down of electric vehicle, around 40% is on the power, related to the battery. In other words, the price of electric vehicle around 30 to 50% is the price of battery. This is show us the importance of battery. If we look at it inside the battery, all of us know that the battery component, the component of battery, sorry, a little bit nervous maybe. So sorry. The component of battery is three main components. There is a cathode, anode, and electrolyte. If we look at the cost breakdown of the inside the one cell battery, around 50% the price of one cell battery is come from the cathode material. The others is anode and others. So it's how important of cathode material. But of course, the performance of battery not only depend on the cathode, but all on the other component. The other things, now if we look at the commercially available battery material. There are several material for cathode. Cathode is very important for battery, not only the cost, but also the performance of battery. Some battery have a specific performance based on the cathode used, but also sometimes the battery, lithium-ion battery, named by the name of cathode material. For example, maybe some of us here, there is LFP, lithium ferrophosphate atau iron-based lithium-ion battery, mean the battery which use the lithium ferrophosphate as the cathode. The others is also LTO. This is named based on the anode material. The other is also there is M.Si. Sorry. M.Si or NCA. This name for lithium-ion battery which use nickel, lithium, nickel, mangan, cobalt, or nickel, lithium, nickel, cobalt, aluminium as the cathode material. So, what kind of material used nowadays? If some company or user require more safety battery, will use the iron-based battery. And nowadays, mostly the Chinese company use this type of battery. Well, the others, if the company or user like to use the battery who has more higher energy density to make the battery size to be smaller and others, the selection should come to the nickel base, either an M.Si or NC. This Korean and Japanese, especially Korean company use this type of, and also we Indonesian maybe will like to use the nickel based battery because we have abundance of nickel source. So if we see that the energy density as battery is the energy storage, so if we see that the energy density is very important, how to increase the density of a battery? There are, of course, there are two ways. Since the energy is the voltage multiplied by the capacity. So to increase the density of battery, there is two selection. Either we should increase the voltage or increase the storage capacity. So if we see what ready in the commercial one battery today, most battery have voltage around 3 volt. The highest one is lithium-ion battery who use the LMNO at 3.8 volt. So to increase the density, we should find or we should use the material who can give the higher voltage of a battery. There are several type of material alternative. This called which we can increase the voltage of battery from around 3 volt to be 5 volt. One of the alternative of the 5 volt generation, some people say also the next generation, is the material based on nickel and mangan with a specific composition. There is lithium, nickel with 0.5, mangan 1.5. Sorry, this should be 0.4, which have voltage around 4.5 volt. This material also named as LNMO. So sometimes this material started as the next generation battery material or 5 volt generation battery material. This is very alternative, but this material still have many challenges. The most problem is if we use this material as cathode material, they have a low cycle performance. very easy to degrade it, to lose the capacity. Why? Because the problem on both cathode and the others is electrolyte. The cathode ones is unstable, easy to corrode and dissolve in the electrolyte. Well, the electrolyte, especially the electrolyte nowadays, when it used in high voltage, easy to degrade, result gas and become problem. So how to stabilize this material? Of course, the alternative is how to stabilize the cathode material and how to modify the electrolyte so can enhance the battery to have a good performance. So in this sense, in this occasion, I will not talk about how to stabilize the cathode material easily by doping and cutting. This is one ceramic one. I will give you one part of our research in near day, how to modify the electrolyte. So, as you all know, that the electrolyte was a compound of three components. First is solvent. The second one is lithium salt as the source of ion, and the third one sometimes use additive. There are many types of chemical structure of solvent, lithium salt, and also the additive. But the most common one for the solvent is used for this is ethyl cyclic carbonate or linear carbonate, something like that. Well, the lithium salt, the most used one is LiPF4 and lithium pyrophosphate. I mean, known as lithium perfluorate, and the additive is something like this. This is the most common use as the electrolyte material. So how to modify this one? Of course, the alternative is how to select the solvent, how to select the lithium salt, and also how to choose the adhesive which is can make electrolyte which I mean sometimes it depends on the type of cathode also. One electrolyte cannot be used with the others cathode. Talking about the salt, there are many types of salt. I mean lithium salt, but the most common salt is this one, lithium hexafluorophosphate, known as LiPF4, LiPF6. Why? Because this type of salt have high ionic conductivity, good electrochemical stability, and others. But this electrolyte is very challenged if we use for high voltage lithium ion battery, because this electrolyte when we use in high voltage easy to degrade, result in HF hydrofluoric. This is very high, very strong acid. It means very corrosive, and especially when meet the water, sometimes also they can react also with water and also with the solvent itself, react to the HF. So if there is high acid in the battery cell, of course the cathode will be have a big problem. So many many method to modify this kind of electrolyte. One of the methods is how to use several types of salt to be blended or mixed and used together. We did some study related with one, but if we check from this 2 decades, many people try to use this one. How to mix to get this one. But not so much study. How to use the blend for the high voltage battery. So I try to make. We try to make this kind of electrolyte by selecting the 3 types of salt which is commonly used. this type of salt is commonly used, but and one to other they have a specific property. For example, the LiBob and LiTSFE, they have a high thermal property but low conductivity, and the others is LiTSF have a very corrosive anode. So we try to combine with three kind of salt and study the effect of mixing. What this new thing we do here is most people make the mixing start from LiPF6 as the best salt. Then they add LSE, LiBob, and other type. So in this study, we try to make the opposite view. We find the most suitable composition between LiBob and LiTSFE. Then we add small by small LiPF6 as the added salt. And we study but the windows, I mean the voltage, oxidation voltage, impedance, and so others. So the type of this mixing salt, when we check the potential windows, I mean the oxidation windows, we can see here that by adding the by mixing the salt and adding the LiPF6, the oxidation voltage increase. I mean a small addition of LiPF6 can increase the oxidation voltage. If we check the impedance, for example, we can see that the addition of LiPF6 to the blends of LiTSFE and LiBob can change the impedance property. The most important, interesting one is a small addition of LiPF6 can increase the solution resistance. In other, increasing the decrease the conductivity, but decrease the transfer the interfacial resistance. So RS can be considered as the internal resistance, but the RCT is the resistance in the interfacial part. Sorry. This is not appropriate testing method, but if we check that electrolyte put in on the separator, the most separator used today is made from polypropylene, which is very non-polar one. If we put the drop of electrolyte, if you can see that the blending will change the property of wettability of the electrolyte on the polypropylene, which is non-polar surface. And if we use that electrolyte as a battery cell, and we assemble cell battery in half cell, I mean using the lithium metal, we can see the property here that the property of the performance of battery is also depend of the type of electrolyte used, and the addition of LiPF6 using the LiPF6 as the additive of the blending electrolyte can increase the battery capacity to be more closer to the theoretical one. We can get here 125 milliampere hour per gram, where the theoretical is 146, around more than 80%. This is for the battery system is acceptable. If we check the retention, the battery, the cyclability of the battery, we very interesting. This is very different characteristic, in which using this small number I mean, 0.05 molar LiPF, a small addition can make the battery to be more stable, have a higher cyclability, more than 50. So more that's the real small addition. I mean, but gave a good impact to the battery performance. So I think time is not so much. It is we go to the conclusion. But as I show you that the battery performance here, I mean the high voltage battery LNMO mostly can be enhanced the performance using the mixed salt as the base of electrolyte. We can see also that small addition, there is some phenomena, but we can conclude that there is some synergic effect between different kind of electrolyte, especially LETSFE, LIBOP, and LFEX mixing. But how the synergic relation is not yet clear. We try to find in the reference, but not yet, still open to be studied. Especially how this electrolyte interact with the electrode, how chemically, what kind of chemical structure happen in the interface or something like that. This still open to be studied. This what can I say in this moment. Last but not the least, let me give you. But next year in near day, our ORNM will have a conference, but related to accelerator, and inside beside this conference, there is also school related to utilization of accelerator for material. So if you have time, please welcome, join us in this conference in next February. Thank you.
Thank you, Dr. Sudaryanto, for the very informative presentation. We move on to the question and answers. We will have around 10 minutes question and answers questions. So if you have question, please mention your name.
market. These days, most of nanocellulose research come from the Japan, but they do not open the resource for their own market. And many of the open results come from the United States or Northern Europe. So one of my friend work in Korean pulp company. Also, they tried making the nanocellulose market, but problems is the same. Paint company or plastic company, they ask to certain kind of the nanocellulose, but the nanocellulose maker only give them general nanocellulose. Each company want a specific grade, but they still they cannot make specific grade for each market. So this delay of the nanocellulose on the market come from this gap.
Okay, thank you. I have another question for Professor Shin. You mentioned about this high pressure homogeneous.
So those high pressure homogenized used more than 100 years for milk making process. And in cellulose, without the big mechanical impact, they cannot separate those microfibril to nano size. So we need very big mechanical impact. So only high pressure homogenized can make those things, but different type of the machine like the microfluidizer or different type of the machine, if high enough the impact on this separation force, they can use those things to making the cellulose nano fibers.
Okay, thank you.
How the degradation happen, it is depend on the type of the electrolyte, of course, but we can see that the voltage also one energy like thermal also. So and also when the battery doing charge and discharge, when the electric appear in the inside, this also thermal happen inside. This thermal can cause the degradation of the organic electrolyte. Maksudnya the solvent is organic. It's not mean the heat happen in during the charge itself can make the source of cause of the degradation. That's why sometimes we find the battery became like pregnant because gas happen inside. The degradation of this organic electrolyte became gas and this try to go out, then became like a pregnant battery. This mostly because of thermal degradation. Thank you.
Thank you for the answer.
The informative session. Thank you for your attendance and participation in the plenary session 3 and 4. Now we may have invited our speakers, Professor Dr. Sin Sujong and Dr. Sudaryanto, to come to the front stage, and the honor of us to invite the head of Research Center for Chemistry, Professor Dr. Yenny Meliana, and one of the researcher from Research Center for Chemistry, Dr. Egi Agustian, to give placard and certificate to the all invited speakers.
Well, ladies and gentlemen, we will have a break time until 1 p.m. But before break time, I will tell to all of you that we will have two parallel sessions at noon. First parallel session will be start from 1 p.m. until 3 p.m. And the second parallel session will be start from 3:15 until 5:10 p.m.
Please join the symposium 10 minutes before the schedule of parallel session for registration. For online participants, all of you are freely to choose the breakout room in Zoom meeting. For our participants, please feel freely to check the schedule and technical guideline in Linktree website.
The first parallel session will divide it into 4 rooms, started with presentation from the invited speaker in each room. Class A of parallel session 3 with the topic of materials, chemistry, and catalysts will be moderated by Dr. Koiria is at room number 2001.
Class B of parallel session 3 with the topic of polymer and macromolecular chemistry, analytical and environmental chemistry with moderator is Dr. Latifa Hauli is at room number 2005. And we have Professor Dr. Ing Insinyur Silviana, Magister of Technique, IPM, as the invited speaker.
Class C of parallel session 3 will discuss related to design process and chemical engineering, biomass and bioprocess engineering with the moderator Dr. Hera Deswita is at room number 2007. And we have Dr. Roni Mariana as the invited speakers.
Class D of parallel session 3 will discuss related to organic and natural product chemistry with the moderator is Mr. Abdi Wira, Ph.D. is at room number TMC 2.3. And we have Dr. Syed Shah Najib Nurul Haq as the invited speaker. The second parallel session will be start at 3:15 until 5 p.m. This parallel session also will divide it into 4 rooms. Class A of parallel session 4 with the topic of material chemistry and catalysis, surface chemistry, and nanoparticles, moderated by Dr. Engineering Muh Nur Khairuwiyadi is at room number 2001.
Class B of parallel session 4 with the topic Analytical and Environmental Chemistry with the moderator Dr. Putri Ramadhani is at room number 2005.
Class C of parallel session 4 will discuss related to surface chemistry and nanoparticles, design process and chemical engineering with moderator is Mrs. Ari Maulifa Hadaputri, Magister of Technique, is at room number 2007.
And Class D will discuss related to organic and natural product chemistry with the moderator Dr. Muhammad Eka Prasetya is at room number TMC 2.3.
For online participants, we will inform you how to join the breakout room in the Zoom meeting. Participant of ISAC ICCME 2023 can select breakout room as follows. Click on More and choose the breakout room menu. Subsequently, the panel room A, B, C, or D will appear, allowing you to select the room that suits your needs by clicking Join.
Alternatively, the host can also allocate you to the designated breakout room from the parallel session based on your Zoom ID, name, or credentials. Hence, kindly adjust your Zoom ID name to reflect your involvement in this conference. We hope all the participants will be joined in each room until the end of this day.
Thank you and enjoy your conference.